The intent of this particular video is to take a look at electroplating, which will be the second half of our lab exercise. What we're going to do in electroplating is essentially we're going to use some electrical energy to coat some object with metal. For example, in the half reaction of reduction of zinc, what we could do with this process is convert our aqueous zinc ions into zinc solid. And in the reduction process, because we're forming zinc solid, that zinc solid we could use to deposit on top of another object or make a layer of zinc solid on that object, which would coat the object with zinc, and that would be the process of electroplating. Now, the driving force behind our electroplating is we're going to use a battery or some power source, which essentially is a spontaneous electrochemical reaction. The battery will determine the direction of electron flow. Given that the battery is a spontaneous process, we're going to see electrons leave from the negative terminal of the battery, and then electrons return to the positive terminal of the battery. So the electron flow is determined by the outside power source, or our battery. Now, because we have electrons flowing out of the negative terminal, whatever object we connect to the negative terminal on our battery is going to be the location of our reduction. Likewise, whatever we connect to the positive terminal on our battery is going to be the location of our oxidation. What's going to occur is our reduction half reaction will take place at whatever is connected to the negative terminal on the battery. The zinc ions that are aqueous, when they touch the surface of the object, are going to form elemental zinc, and that would coat the object with a layer of zinc as it gets formed during the reduction process at the object that's connected to the negative electrode. This would be electroplating that object, in this case with elemental zinc. Meanwhile, at the anode, or location of oxidation, what's taking place at the oxidation half reaction is it's going to convert elemental zinc into zinc ions, which replenishes the zinc aqueous ions in solution. That way we get a cycle of zinc ions coating the object through the process of reduction. Simultaneously, the aqueous zinc ions are getting replaced by a piece of metal zinc being oxidized into aqueous zinc ions. And this completes the cycle for our electroplating process. Let's take a look at an example problem. Here we have 0.80 grams of zinc are going to be electroplated in 180 seconds. How many coulombs are transferred during this process? Our first step is writing the reduction half reaction for the reduction of aqueous zinc ions to elemental zinc. We want to notice that this is in a 1:2 ratio, indicating that for every 2 moles of electrons that get transferred, we're going to deposit or reduce 1 mole of zinc ions to elemental zinc. We can use a proportion to solve for how many moles of zinc are getting deposited in our problem. Solving for x gives us 0.012 moles of elemental zinc are being deposited during this process. In our balanced equation, again, for 1 aqueous zinc ion, 2 moles of electrons are transferred to create 1 mole of zinc. Therefore, the amount of electrons being transferred is double the number of moles of solid zinc being deposited. If we take the number of moles of zinc times 2, that'll give us how many moles of electrons have been transferred. It says, therefore, 0.024 moles of electrons got transferred during the process of depositing these 0.80 grams of zinc. Faraday's constant is the number of coulombs on 1 mole of electrons, which is 9.648 times 10 to the 4th coulombs per 1 mole of electron. We can use that with a proportion to find out how many coulombs have been transferred when we have our 0.024 moles of electrons transferred to deposit our 0.80 grams of zinc. Solving for X gives us approximately 2,300 coulombs were transferred during this process. The next question asks us what current will pass while this electroplating process took place. Now, current is measured in amps. An amp is the flow of 1 coulomb of charge per every second, would be the same thing as 1 amp. We can use a proportion to solve. We know from the first part of the problem that we had 2,300 coulombs of charge transferred, and the time we were provided is it took 180 seconds for that charge to be transferred. So if we have 2,300 coulombs being transferred in 180 seconds, we'd have X coulombs being transferred in 1 second. The number of coulombs per 1 second would give us our amperage or our current. Solving for X gives us roughly 13 coulombs per second, or we'd have a current of 13 amps in this situation during the deposition of our solid zinc. Now our voltage, 1 volt is the same thing as 1 joule per coulomb. Here we're saying the applied voltage was 6 volts. How much energy was utilized in this electroplating process? The 6 volts that were given is the same thing as 6 joules per 1 coulomb. We can use this to set up a proportion. If we know we have 6 joules per 1 coulomb, we're going to have X joules of energy consumed for the transfer of our 2,300 coulombs from earlier in the problem. Solving for X, we get 13,800 joules of energy were utilized in the deposition of our zinc. The last part of the problem, we use a conversion. We have 1 kilowatt hour of energy is the same thing as 3.6 times 10 to the 6 joules of energy. So we'll get X kilowatt hours for the 13,800 joules we've utilized in this problem. Solving for X, we find that this process consumed 0.0038 kilowatt hours of energy, depositing our 0.80 grams of zinc.